Definition and conditions for similarity of triangles. Welcome, everyone. Today, we are going to begin a new topic in our geometry unit, the definition and conditions for similarity of triangles. To start off, let's look at the concept of similarity. In our previous lessons, we spent a lot of time studying congruence. You'll remember that when two figures are congruent, they are essentially carbon copies. They are identical in both their shape and their size. However, similarity is a much broader and more flexible concept. When we say two figures are similar, we mean they share the exact same shape, even if one is much larger or smaller than the other. Think of it this way: one figure is simply a scaled version of the other. Now, while this rule applies to all polygons, today we are going to focus specifically on triangles. Because a triangle is just a specific type of polygon, all the general rules of similarity we are about to discuss will apply directly to them. As we move through the next few slides, we will look at the specific mathematical conditions you need to prove that two triangles are indeed similar. Conditions for similarity of triangles. Now that we have established the basic idea that similarity is all about having the same shape, even if the size changes, let's look at the specific rules we need to follow. It isn't enough to just look at two triangles and guess. For two triangles to be mathematically classified as similar, they must satisfy two fundamental conditions simultaneously. This means both rules must be true at the same time. To make this clear, let's consider two specific triangles. Triangle ABC and triangle PQR. We can say these two triangles are similar if the following conditions are met, which we will break down in the next two slides. Equality of corresponding angles. Now that we have established that two triangles must satisfy two specific conditions to be considered similar, let's dive into the first requirement. The first condition is that the corresponding angles of the two triangles must be equal. Think of this as the shape-preserving rule. By ensuring the angles are identical, we ensure that the shape of the triangle remains exactly the same, even if the triangle itself grows or shrinks. To express this mathematically, we look at the vertices of our two triangles. Triangle ABC and triangle PQR, we must be able to state that angle A equals angle P, angle B equals angle Q, and angle C equals angle R. Once we have confirmed these angles are equal, we can move on to our second condition, which deals with the lengths of the sides. Proportionality of corresponding sides. Now that we have established that the angles must be equal to maintain the same shape, we need to look at the second essential condition. It isn't enough to just have the same angles. We also need to ensure the sides are scaled correctly. The second condition is that the lengths of the corresponding sides must be in the same ratio. You might hear this ratio referred to by another name, the scale factor. Think of this as the multiplier that grows or shrinks the triangle. To see how this works mathematically, let's look at the equation on the slide. We take the length of side AB and divide it by its corresponding side, PQ then. We take side BC and divide it by side QR finally. We take side AC and divide it by side PR for the triangles to be truly similar. All three of these fractions must be equal to one another. If even one of these ratios is different, the shape will be distorted, and the triangles will not be similar. Notation for similarity. Now that we understand the two fundamental conditions, equal angles and proportional sides, let's discuss how we actually write this down in a mathematical sentence. This is called notation. When we want to state that two triangles are similar, we don't write out the whole definition. Instead, we use a special symbol, a tilde, which looks like a small wavy line. This symbol, pronounced is similar to, denotes the relationship between the two shapes. For example, if we have triangle ABC and triangle PQR, and they meet all our criteria, we write, triangle ABC is similar to triangle PQR. Now, I want you to pay very close attention to this next part, because it is a common pitfall in geometry. The order of the letters in this similarity statement is absolutely crucial. It isn't just a random list of vertices. When we write triangle ABC is similar to triangle PQR, that specific order carries a mathematical promise. It implies a direct correspondence. It tells us that vertex A corresponds to vertex P, vertex B corresponds to vertex Q, and vertex C corresponds to vertex R. Keeping this order in mind is vital, especially when we move on to applying these rules to real-world scenarios, like the architectural blueprint example we are about to see. Real-world example, architectural blueprints. Imagine an architect who is tasked with creating a small-scale blueprint of a triangular park. In this scenario, the actual physical park can be represented by triangle A, B, C, and the small blueprint on the paper is represented by triangle P, Q, R. To make sure this blueprint is actually useful, we need to follow the two conditions we discussed in the previous slides. First, let's look at step 1, maintaining the shape through angles. As we learned earlier, for two triangles to be similar, their corresponding angles must be equal. To ensure the blueprint is an accurate representation of the park, the architect must ensure that the angles of the blueprint triangle are exactly the same as the angles of the actual park. For instance, if the actual park has an angle of 60 degrees at vertex A, then the blueprint must also have an angle of 60 degrees at vertex P. By doing this, the architect satisfies our first condition, the equality of corresponding angles. Next, let's move to step 2, scaling the size through sides. Now, obviously, the actual park is much larger than a sheet of paper. To represent it, the architect uses a scale, let's say a scale of 1 to 100. This means every side on the blueprint will be 1/100th of the actual side in the park. Let's look at some numbers. If the actual sides of the park are AB equals 100 meters, BC equals 200 meters, and AC equals 150 meters, then the blueprint sides will be calculated as follows. PQ equals 100 divided by 100, which is 1 meter. QR equals 200 divided by 100, which is 2 meters. And PR equals 150 divided by 100, which is 1.5 meters. Finally, in step 3, we perform the verification of the ratio. We need to check if the sides are truly proportional, as we discussed in the second condition. Let's check the ratios of the corresponding sides. AB divided by PQ equals 100 divided by 1, which is 100. BC divided by QR equals 200 divided by 2, which is 100. And AC divided by PR equals 150 divided by 1.5, which is also 100. Since the ratio is a constant 100 for all three pairs of sides, we can confirm that the sides are proportional. Because we have met both the angle condition and the side condition, we can mathematically conclude that the blueprint, triangle P, Q, R, is similar to the actual park, triangle A, B, C. Now that we have understood the theoretical conditions for similarity, let's see how this applies in a real-world scenario. Before we move on to some common mistakes to watch out for, let's keep this idea of scaling in mind, as it is the heart of similarity. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the definition of similarity, it is very easy to make certain errors in your proofs and calculations. Let's look at 3 specific mistakes to avoid. First, many students often confuse similarity with congruence. You might see the symbol for similar, which is the tilde, and accidentally treat it as the symbol for congruent, which is the equals sign with a small congruent symbol on top. To keep this straight, remember what we discussed in our introduction. Congruent triangles are identical in both shape and size. They are perfect clones. However, similar triangles, as we've seen, are identical in shape, but they are not necessarily the same size. One is simply a scaled version of the other. Second, be very careful not to pair your sides incorrectly. A common error is to pick sides at random and try to create a ratio. To avoid this, always pair sides that are opposite to the equal angles. For example, if we have established that angle A is equal to angle P, then the side directly across from angle A, which is side BC, must be paired with the side across from angle P, which is side QR. If you don't follow this rule, your scale factor calculations will be incorrect. Finally, never ignore the order of the vertices in your notation. This is a crucial point. Writing delta ABC is similar to delta QPR is mathematically different from writing delta ABC is similar to delta PQR. The order of those letters isn't just a convention. It is a map. It tells you exactly which angle corresponds to which and which side corresponds to which. Always double-check your vertex alignment to ensure your similarity statement is accurate. Keep these points in mind, and you'll find that working with similar triangles becomes much more straightforward. Key takeaways. First, remember the core definition. Similarity simply means that two figures have the exact same shape, even if their sizes are different. Think of it as a scaled version of the original. Second, it is vital to remember that for two triangles, such as triangle ABC and triangle PQR, to be mathematically similar, two specific conditions must be met simultaneously. The first condition is the equality of corresponding angles. This means angle A must equal angle P, angle B must equal angle Q, and angle C must equal angle R. This is what preserves the shape. The second condition is the proportionality of the corresponding sides. This means the ratio of side AB to side PQ must be equal to the ratio of side BC to side QR, which must also be equal to the ratio of side AC to side PR. Third, pay close attention to your notation. When we want to state that these triangles are similar, we use the tilde symbol, which looks like a small wave, written as triangle ABC is similar to triangle PQR, and as we discussed earlier, always keep your vertices in the correct order. Finally, keep in mind that this constant ratio we found between the corresponding sides is a very important concept called the scale factor. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear in your mind. If you have reviewed these points and feel confident, you are well prepared for our next lesson, where we will apply these rules to solve more complex geometric problems. Great job today!